So this talk and a lot of my work is basically on belongs to the body of work about applications of convex optimization to some classical problems in theoretical CS. And the theme that I wanted to touch on today is to study the choice of whether you use a linear formulation of the problem that you have or you use a convex formulation. So I like to keep my talk informal, so feel free to stop me whenever you want. All right. So one of the oldest ideas in TCS for solving a problem is to consider a continuous relaxation of the problem. So to do it, you usually model your problem as a linear or convex program, and you just use one of your favorite convex optimization primitive to do it. So if you're into second order method, there's simplex, interior point, ellipsoid from the 70s and 80s that you can use. So you can use that to solve LP relaxation. So more recently, people have started looking at the potential of using first order methods for solving these programs, and they have gotten some of the most fantastic results of the past decade. So to give you like an example of a linear relaxation and a convex relaxation. So here's like a very, the most classical application of linear relaxation. So it's the maximum bipartite matching problem. So you have a bipartite graph, and you want to find a maximum cardinality matching. So the LP relaxation that you use for this problem is just to model your matching constraint as a linear constraint. So you don't want to measure vertex more than once, and you want to maximize the size of your matching. So pretty classical, pretty basically Hungarian stuff, Hungarian algorithm. People like Edmonds have worked on this kind of things extensively, back in the 70s and 80s.
Even earlier, I think, 50s.
Yep.
Hungarian method?
From Jacobi. That was called Hungarian, real Jacobi.
So when was that?
I think there was some paper by
If I remember, like 1900, 1800?
Yeah, he found out from Jacobi exactly worked on this problem. I had a solution, but
Goes way back.
Yeah, it has a long history.
The point in that essay is that I guess even Jacobi was Hungarian. Like, Kuhn himself is a kind of, his point is truly Hungarian.
So it's like humans have Hungarians as like origins.
So this is an example of LP relaxation for solving a discrete problem. All right. So historically convex relaxation or convex formulation came like a few decades after. So the first famous example for doing something like this is really for the max cut problem. So you have a graph, an undirected graph, and you want to find a cut that causes the maximum number of edges. So again, you have a relaxation for this problem, and it's based on this vector programming, or it's a type of convex programming. So I'm not going to get into details, but basically this constraint just says that basically whether you want to put a vertex on one side or the other side, if vertices with +1 is going to stay on one side, and -1 is going to stay on the other side. And you can verify this formula just computes the number of edges across a cut. So it's a relaxation of the problem, and Goldman and Williamson used it to get like the first non-trivial approximation algorithm for solving the math cut problem. It's still the best, even to this date. So you have all these linear and convex relaxations, and the message that I want to get across today is, if you are given a problem, it can actually make a huge difference. How you model your problem as a convex or linear program, and how you apply one of these continuous methods. So that's the overarching theme that I want to get across today. And maybe somewhat surprisingly for certain problems, you can get something cheap very easily just by considering a different formulation of the problem. So in particular, I want to touch on this paradigm between whether you want to use linear relaxation or convex relaxation. Well, of course, a linear relaxation is a convex relaxation. But the point I want to get across is whether something that you use for something that you traditionally use LP to solve can enjoy some benefit of going to the convex side. So more specifically, I want to understand whether certain problems admit faster algorithms by using like a convex relaxation instead of a LP relaxation. And the answer is yes. And there have been a few examples of this in TCS from the past few years. So the first one is probably very famous. I think more than half of the people here have heard about it. So a few years ago, a bunch of people from MIT and this guy from Berkeley, Sherman, they got like a almost linear time algorithm for solving math flow, but at the expense of approximation. So it's not exactly the math flow problem you see in your algorithm 101, but it's an approximate version of it. So they show that if you are willing to suffer some approximation loss, you can actually get a very fantastic result, pretty much the best that you can hope for. And another example is and they do it just by using some first order method. So math flow you can just solve it using LP because it's a linear program. And the second example is about positive LPs. So LPs with only basically non-negative coefficients. So Zion and Lorenzo, and in a follow-up work by D. Satush and Mahoney, they show that for these kind of problems, you can also get like a linear time algorithm at the expense of approximation. And they do it. They also did it by switching from basically linear to convex programming. So it's an LP, you can solve it. Well, of course, using an LP. And the message that they got across is you can actually get a faster algorithm by going convex.
And here, when you say approximate, you're approximately satisfying constraints also.
So for that case, you can actually just use approximation in the objective function. So you can satisfy the constraint exactly.
You can scale down, right?
Yeah, that's basically the trick. So if you're into this kind of stuff, there's also this mixed packing coupling.
Yeah.
For that case, you have to use approximation in the constraint. For pure packing or pure coupling, you can just scale down or scale up.
No, but you say only positive elements. They are not necessarily packing or covering.
Yeah, I guess I was being lazy or a bit sloppy.
So it is only packing or covering.
Yeah, yeah.
Because positive LPs is much broader class.
Yeah, we still
I don't know.
we still don't know if we can get like a linear time algorithm for
Right.
mixed packing coupling.
Yes.
D and Satish are still working on it. Maybe we'll have hear something great in a year or two. Other questions? All right, so we've seen two examples where approximation helps. So for this approximate version of the problem, we can get a provable speed up by going convex. So a natural question is whether you can do something similar for exact problems. And that's part of the talk of today. So I'm going to show you two problems where you can get like a speed up by going convex, even in the exact paradigm. So for this problem in econ and this problem in discrete optimization. And I also want to give you an example where approximation helps. So it's an approximate version of a problem from geometry.
But one question. So when you say convex relaxations are like better for some problems, what do you mean by solving packing LPs using convex relaxation? What does
I would say it's more like you have this LP, but you want to consider kind of like an equivalent convex formulation of it.
I see. Like you want to say that you can solve set cover like faster using some convex.
So for that case, like you don't really get something specifically for discrete problems, because say for things like set cover, you only get a fractional solution by solving the corresponding LP relaxation. Right?
Yeah,
So it's not
still
exactly
talking about fractional.
okay. Yep. So and the first thing that I want to touch on is a problem from economics. So this equilibrium computation problem. And so for the first two problems, I'll kind of be very high level, only highlighting the key idea. For the last one, I'll actually give like a very simple cube proof of a basic result, but I won't go into full details. So it's based on a very simple economy by Lisa and Sagel. So one of the most prominent problems in econ is whether how you can get to equilibrium. So if you have an economy, why does it converge to an equilibrium? How do prices become what you observe? How do supply and demand come into a picture? But the full picture, some of you probably know, is computationally hard. So what Lisa and Sagel look at is like a very simple economy where you can get some algorithm for finding an equilibrium. So in this very simple economy, we only have two things. We have a bunch of items or goods that you want to sell, and we have many people. So it's not quite what you see in real life, because the supply is going to be fixed in this case. So given this very simple picture, how do we get an equilibrium? So that's the question that I want to talk about. You will set the price too high, you are going to undersell. So certain goods may not be sold. If you set it too low, too many people may want, this pen, and you have like an over demand. So to do it, first I need to set up some notations. It's pretty much the only slide that has a lot of math or notations in it, so bear with it for a moment. So first we have the items that we wanted to sell, so we call that V. PI is the price that we want to set for item I. And for the right-hand side, we have the people. Well, we are dealing with an economy, so it's important that we actually have access to the players in the economy. So we just model them by a very general valuation function. So we have this function that specifies how much a bundle of items is worth to you. And finally, given prices on all the items, a buyer is just going to maximize his utility, which is defined by the valuation minus the prices of the items. So we can't assume the valuation and the prices are on the same unit. So this is the setting. So given the valuation function and all the goods, how do we get an equilibrium? So Mathematica, that just says that you just want prices on all the items such that the maximizer for the buyers across the economy exactly partition your set of items. So there's another way of saying that the market clears. You don't have over demand, you don't have oversupply. So Lisa and Sergey gave LP relaxation for this problem. So I'm not going to get into how you actually derive this LP. But basically, the thing that you want to observe is that you have a constraint for each bundle of items and each buyer. Yeah.
We make some assumption about the value function, because I can imagine situations where every buyer has negative marginal utility for adding some item to their set, in which case even if I set the price to 0, that item's not going to clear.
Yeah, I'm actually cheating a bit. I didn't get into the full details, but so in the full picture, the prices can actually be negative. So, and you have all these issues about the existence of equilibrium and so on. But but for today, I just want to focus on how you can get a better algorithm by going convex.
So sorry, what's wrong if I set all prices to 0?
Nobody buys the item.
Item has negative utility. Even if prices are 0, then nobody's going to buy it. But
So
then
you can't argue that there
So
will always be
precisely
the
that
same
has to do with
Yeah.
the equation.
yeah, exactly. But then prices will also have to be negative if items are negative.
Yeah, it's
They're
like
negative
like-
externalities, so then there are financial.
I'm sure algorithmically it's interesting, but from modeling perspective, that's like
No, it is. So there are some items with
Weird.
negative
Yeah.
externality.
yeah.
So like
One example.
garbage, you want garbage to clear, so you have to pay someone
so
to
you
take
bundle
the
like
garbage.
iPhone and garbage.
There's no bundling, so you have to pay people
That's also
to
part
take
of garbage.
garbage. So that's
The
what it
iPhone.
means. So yeah, negative price is a negative utility.
Like pollution.
Economically also it's
like in Soviet times, you buy a good book, and as a bundle, you get also several like books that otherwise no one would buy.
Here there's no bundling.
Yeah.
So there's no bundling here. Each item is priced separately.
Okay.
Yep. So it's just a very simple setting. So it's like a very simple economy. I would say So the way I see it is more like a first step towards understanding, what you can do for more general economy.
So I also have another question, just so that I understand the problem correctly. So each buyer chooses best subset according to his valuation, and then you require this to be a partition.
Yep.
So in particular, number of buyers must be smaller than, or you are saying that even though number of buyers might be larger, many of them can get empty set or something?
Yeah, they can. I mean, this is like a special case of what I did in the paper. So in the paper, you can actually have multiple copies of the same item.
I see.
So that's a bit more realistic. Otherwise, if most of the people don't get anything, that's kind of, strange. Yeah, so don't worry too much about the form of this LP. But so the feature I want to highlight is that this LP has exponentially many constraints because you have exponentially many bundle of items. So to solve something like this, you need a separation oracle for each of the constraint, and this oracle makes sense economically. So you will want to separate this. A very natural way is to just say that you can solve this problem. So if you can solve basically the utility maximization problem for each of the buyer, you'll be able to tell if a solution UP is feasible for your LP. So as a corollary, if you have this, what we call the demand oracle for each buyer, you will be able to get an optimal solution to this LP. And that optimal solution is going to be the prices that you want. So far, so good.
Just another question. So basically, this LP formulation, it doesn't assume anything about VJ. It could be like literally any function. You don't assume any submodularity or anything.
Nothing. Just a general valuation function.
So as soon as you can maximize this thing, it's like solvable at least.
Yep.
So when this implies what condition, what solution will imply market clearing, for example? You saw this LP
The
to the market clearance.
So that's the thing I didn't want to get into.
Okay.
Yeah. So you have to, but I can show you how to do that after the talk. But I promise you, it's just a few lines.
Yeah. No, I think what I was asking is, so if you solve this, not why this gives market clearing, what is it? Just you solve this and then the solution is market clearing.
Yeah.
Yeah, that's what I'm asking.
Yeah. Well, the actual
In the fractional sense.
it's actually in the integral too.
No, you
So
find
the variables are fractional, that's okay.
Yeah.
You get the prices out of this.
Yeah, but allocation is not.
Yeah, but that's fine. Allocation is not a variable here.
Yeah. So this formulation isn't going to solve the allocation problem for you.
Or
Oh,
is it
I
the
see.
price?
Okay.
Or is it the solution of the price will give you the market clearing price?
Yeah.
But you need to get your partition separately.
Yeah.
And then you solve that max for each of them separately.
Okay, that is good.
Yeah.
There
You
are
will.
time-taking issues and all that.
Yeah.
Then in the interest of time, I think we should move on.
And P of S is like linear function, so it's sum over.
P over.
Yeah.
Oh yeah, it's just a sum of all the prices. Yeah. Just a shorthand. So there are like two things that I'm not happy with this solution. So the first thing is, we can't touch on that, is a market, and you seem to be assuming too much if you know specifically about each of the buyer. I don't know what you guys want, right? And no one does. So and the other thing is that this LP has a variable for each buyer and each item. So the total number of variables is going to be the sum of the number of items and the number of people. From an algorithmic perspective, this is not that satisfactory because we have 7 billion people on the planet. Relatively, we don't have that many types of items. So algorithmically, the dimension of this LP is going to be very huge. And and I argue that you can bypass these two issues just by going convex. And it's very naive. So you look at this LP. So if at the optimal solution, well, you're minimizing U. So you want to set U to just be the maximum of this guy over S. So you set that, and you just replace U by this maximum of a bunch of linear functions. And that's the convex formulation we have. So we just wanted to, we have this function of P with the same objective function. It's not a hard thing to check that it's actually convex. And more nicely, so if we want to apply any kind of convex optimization primitive, we need the subgradient or the gradient. And in this case, it's actually something really nice. So taking the gradient of that guy, you can show that you can get the gradient by what we call what economists call the aggregate demand. So you just have the solution to our maximization problem as a multiset. So you have a solution for each of the bias, but you don't need to know the solution for individually. You just need to know the direct sum of these solutions. And now if you have that, you can just minimize F by ellipsoid, or let's say you can also use first order method to do it, like subgradient descent. And that kind of bypassed the issues that we talk about. So for this convex formulation, well, we just have the prices P. So the dimension is just equal to the number of items. Whereas before, we also have a variable for each of the people in the economy. And this is bad because this is typically a lot larger than the kind of things that we can buy. In terms of how we interact with the economy, for the linear case, we need to understand each of the bias really well. We need to understand how to solve their utility maximization problem. Whereas for the convex case, we just need to know how to solve these problems as a whole over the economy. So it's a very simple example to show that how some small change in your formulation can actually give you a significantly better or more general result. And that's the message I want to bring across today. So how you model and how you apply these methods can have a significant impact on your solution.
Sorry, what's the improvement? Like the running time improves, or
You can get a better running time. So we all in the actual paper we had like a few other tricks, but here you can already see a better running time because the dimension is smaller.
So you apply
but you're solving a Convex program, so it's, I don't know. I mean, I don't know the exact running times of these algorithms.
So for
I will trust you that it improves
Yeah.
the running time.
So for cut and plane or ellipsoid, the cost of solving linear or convex program is actually the same, pretty much the same, essentially the same.
Since these are exponential variables, you are anyway using one of them.
Yeah, you did.
So but basically I was asked, so you just formulated this problem like sum of maximums, so it's really not smooth. So you need either like some gradient based method or like ellipsoids or something like this.
Yeah.
So is there any way to smoothen this maximum using something?
You need to make more assumptions about the problem. I mean, just by the model itself, V is arbitrary, the valuation is arbitrary. So you can't really smoothen it to get any meaningful guarantee, I would say. But I'm not entirely sure.
Then you might have to lose instead of exact might have to go approximate.
And so the second example for today is a problem from geometry. It's not quite the same as before because in this case we are just we'll be happy with approximation. And it's kind of basically inherent to the problem in some sense, and you'll see why. So some of you may not recognize the name, but it's the Caratheodory theorem is a simple fact from LP and Convex geometry. So if you have a point in a polytope, you can represent it as a convex combination of the vertices, and you can do it in such a way that you only need the dimension number of vertices, essentially. So that's Caratheodory theorem, and that's something we learned in grad school year 1. We know that it's tight because you can just consider a triangle. But the problem I want to talk about is an approximate version of this result. So what if you just wanted to get this point approximately? So you have so in this case, in this picture, you have your target U. What if you just want to represent U approximately? So if I'm happy with something close to U, I may be able to get away with fewer points, fewer vertices of a polytope in the convex combination representation. And this is what Sid Bauman proved a few years ago. So he proved that if we're happy with approximation, you can get basically dimension independent bound on the number of vertices you need. So you depend on your error and also on the basically distance of your polytope, how big is it. So in this,
Why do you say this was proved by Bauman and not Moret?
So Moret proved it for a substantially more general setting. In functional analysis. So what happened? What happened is that Bauman proved this, and then after, so he didn't prove it just for the sake of proving such a result. He actually has some application to game theory in mind.
I thought Maury proved it for L1 only. Actually, is it not true?
Say that again.
So
Sorry.
what's called Maury's empirical method, it's for L1, or he also proved LP bound.
He is over hyperspace. I don't understand the statement.
Okay.
Yeah, it's something very general.
Yeah, Vershinin quotes it in his, but I think he shows only like L2, 1. Yeah, okay, anyway.
I think it's only L2.
Okay, L2.
But you can get LP by the smoothness of
Yeah.
Like this dependence?
Yeah, that's basically what I'll talk about.
So was it constructive?
It is made constructive now.
No.
But it was made constructed in the 90s actually.
In the 90s.
Original
Okay, then
proof
you
is
want the
By Andrew Barron.
Now, Berman's proof is also not constructive, but there is a paper, follow-up paper, which made it constructive. That was also known. Anyway, the proofs are different, so I think.
Yeah. So, and everything is measured in LP norm, just as people have said. So, let's just set up some notations before getting to the actual math. So we have our vertices Vi, and for convenience, we just represent it as the columns of a matrix V. So again, we have the bound. We have a bound on the size of the polytope, and we have our target U, which is a convex combination of the vertices. The problem we want to solve is to get a k-sparse vector in the unit simplex. So a k-sparse convex combination, such that we approximate our target sufficiently well. So Bauman's proof or Murray's proof is very cute. Basically, you just represent your point. You just so you have the convex combination, and you just see it as a probability distribution. So you can you pick Vi, a vertex Vi with probability lambda I, and you just keep doing it for some number of steps. So you have this many samples, and that's it. You just output the average of it, and it clearly matches our targeting expectation, and you can prove using some concentration inequality that is sufficiently good to satisfy our requirement. So
I think attributing this proof to 2015 is just clearly wrong. So this is something from like convex combination that was known long ago.
Yep.
Yeah, that's more.
Yeah, precisely.
So two things about this method. So it's randomized because you are sampling from a probability distribution. And the second thing is, I think, a bit of a over-assumption. So you need to know the coefficients, lambda I, in order to sample from the distribution. And so I want to argue that you can get away with these two weaknesses by going convex. So if you go convex, it's a convex objective. So the natural way of doing it is just to minimize our objective. So to minimize it using convex optimization, again, just as before, we need to know the gradient. But in this case, the gradient isn't something very nice because it's the p norm. So you can try to do it, and it's going to get stuck somewhere. So our method is not something very new, but it's basically to look at the dual. So if the primal is too hard, sometimes you can get away with it by going to a dual, which can be nicer. So we just go to a dual. So we replace the LP norm by the corresponding maximization problem involving the LQ norm. So you have a Y. The optimum solution is going to match what we have here, and we just swap the max and mean. People have done something similar for many other problems, like getting a solution to a zero-sum game. And so our observation is that it's actually significantly simpler to study this function, to optimize this dual function. I'm not going to get into the details, but the reason you can do it is because the gradient of this guy is something very nice. It's basically a linear function in x. So if you minimize it, you are just going to get what we have here. And given y, we know that the excuse me, the minimizer x is going to be a basis vector, because you are just minimizing this guy. So in this sense, if you are using something like mirror descent, you'll be able to get some sparsity guarantee, because each of the iteration you just kind of increase your sparsity by 1. I won't have time to go into the math, but if you just write out your standard mirror descent guarantee, you can get the sparsity from the number of iterations. And you can get our requirement that this U is close to a sparse Convex combination by the optimality guarantee. Nothing fancy, it's just all straightforward computation.
And if you were doing Frankfurt on the naive objective function, it wouldn't give you the same?
I think you'll give it the same. Yeah, it's basically this result.
So I think this is again due to Andrew Barrow design.
Yeah, basically we wrote the paper, we didn't realize. But we did credit him in the final version.
Actually, Berman also credits it in his talk paper. He says that this proof is not the only focus
Yeah.
on the application.
Yeah, he didn't know about it before.
Yeah. But in the version, he does not take credit for it.
So what's the running time after all?
So you are just basically this guy, the number of iterations.
Times like linear and everything.
Yeah.
So what's the cost per iteration?
You are just doing like a gradient, like mirror descent step, so linear. So from an algorithmic perspective, this is kind of nicer than before. It's fully deterministic, and you don't need to know the coefficient in the Convex combination.
How do you get this dependent linear and P? Like, what's the source of it?
Strong convexity of LP norm. So,
I see.
so the Berman divergence we use in mirror descent is just the LP norm. So there you get like the P from there. Okay. And we did some simple simulation, so to compare the two methods. So the lower part is the Convex formulation. So you see that even in terms of performance, it's about an order of magnitude better than the naive random sampling method. And
what are the x's?
so it's sparsity versus the error. Sparsity error. So for the same sparsity, we get a better error.
Y-axis is in log.
Yep. All right. Are there questions about this problem?
How about 10 minutes?
Yep. So I'm a bit running out of time, so I'll try to cover most of the main application. I really want to get to the proof. So bear with me for a moment. So I'm going to give some details, but you'll be able to see the main application of Convex method to it. So for this problem, again, we see that we can get like something better by considering a Convex formulation of the problem. And it's not even hard. You just take the Convex, the dual, and that's it. So the last problem I want to touch on is the submodular function minimization problem. And before I get into details, I need to actually need something about the ellipsoid method to do the Q-proof that I've been talking about. So it's just a very quick recap of what everyone here has seen before, maybe many years ago. So the ellipsoid method, you have a target set K, and the problem is that we want to find a point in our set K. So what we are given is a separation oracle. So if you have a point, either you know that it's in your target, or you have a hyperplane separating your point from the target. And so that's our problem. So to one ellipsoid, we just find a find a very big ellipsoid containing our target K. And we basically just keep covering the separation oracle on the center of the ellipsoid. So we have the center here. You find a hyperplane separating it from the target. And we just keep doing it on the other half. So for the second step, we want to keep applying it. So we find an ellipsoid containing the remaining feasible region. And center again, separating hyperplane, the new circumscribed ellipsoid. Again, here we're lucky, we just find something in our set in a few iterations. So this is what Karchan proved for the ellipsoid method. So he formulated the ellipsoid method, and he basically proved n² time convergence by arguing the volume of the ellipsoid is going to decrease at a rate of 1 minus 1 over n. So to get our result on submodular minimization, I need something slightly stronger. So so after Karchan proved his result for the ellipsoid method, there have been a few follow-up, and and some of the algorithms after can actually achieve a better convergence rate. I'm not going to get into the details there, because they are a bit complicated to describe. But you can get the intuition by this, fact about the center of gravity of a polytope. So if you have a Convex set, and you find a hyperplane passing through the center of gravity, so a standard fact in Convex geometry says that you have a constant fraction of volume for each of the two subsets. So any hyperplane passing through the CG, center of gravity, is going to divide the two halves in the ratio between 1 over e and 1 minus 1 over e.
I remember asking this question, but I forgot the answer. What's the example when this bound is tight? Is it like cylinders?
I think like a cylinder.
No, when
This green bound theorem is tight.
I forgot.
you mean the 1 over e?
Yeah.
I think like a cylinder or something like that.
Cylinder, okay.
No, not the same. Cone.
Cone.
Yeah, I don't remember, to be honest. Yeah, so if you don't use ellipsoid, but use the center of gravity as your iterate in the algorithm, you immediately get a faster convergence, because instead of 1 minus 1 over n, you have a constant rate of decrease.
Why do you say that you need n iterations? It means that like inscribed both versus
When your feasible region gets small enough.
n times larger?
Exponentially small. You want.
Why is that?
If you have a ball of radius epsilon, you
1
start
minus 1
with
over
a
e
ball
to the
of-
n.
Oh, I see. Okay, because volume decreases by constant factor.
Yeah.
Okay.
Okay. So we'll see how. So in particular, you can apply it to solving Convex minimization just because your subgradient is going to give you separation from the definition. So that's everything we need about the cut and play method or the ellipsoid method. And I have 5 minutes to do the submodular part, so I'll try my best. The actual proof is very simple. I just need to set up some, the framework to do it. So submodular functions are basically these things where we have the measure marginal return. So it's a discrete function on over a discrete set. So whenever you add something to a set, the value is going to be smaller than, it's going to be bigger than what you will get when you add this guy to a bigger set. The actual definition doesn't matter that much, but it basically captures what you see about this dimension marginal return stuff from economics. It's a discrete analog to that. All right. So and the SFM problem is just to minimize the submodular function. Well, we need to make some assumptions about how we represent the function because it's a discrete. It's a function over exponentially many subsets. And the standard way of doing it is just to have access to the function values. So you give an oracle a subset, the oracle is going to tell you the value of that subset. And it has many applications that I'm not going to get into. But the two things. So for discrete algorithms, there are two kinds of polytime notions that we care about. The first one is the Wiki polytime algorithm, so something like interior point or ellipsoid. The running time is going to depend on the bit complexity of the problem. And the second type of guarantee is independent of the bit complexity. So it just depends on the dimension of the problem. So our result, so for this work, we got like a basically n squared time faster algorithm than what people have done before. And going back to our convex versus linear paradigm, we pretty much got this result by considering the convex relaxation of the submodular minimization problem instead of the standard LP relaxation of it. Well, I won't get into the full details, but I will try to convey the intuition by the means of a very small, cube theorem. So I'm just going to tell you how you can minimize a submodular function without making too many calls to your oracle. So I'll tell you how you can minimize such a function using just cubic number of oracle calls. The best bound from before is n to the 5. So you can get something cheap just by going convex. So there's a LP relaxation before. The actual formulation doesn't matter for our purpose. So again, to apply any kind of convex programming method, we need to have a convex relaxation of our problem. And for some modular function, the convex relaxation that we use is going to be something very natural. So if you have a function, you basically just take the hyperplane supporting the epigraph of such a function. So you just make the function convex by smoothing out the concave regions of it. So Lowas was the first to consider such a relaxation, and he proved that the subgradient of f hat, the Lowas extension or the convex closure, can basically just take linear number of oracle calls. So in linear number of oracle calls to your evaluation oracle, you can compute the subgradient. That's the only thing we need about the Lowas extension or the convex relaxation of submodular functions. We are not going to make any connection to submodular functions anymore. And that will suffice for our purpose. So we talk about the ellipsoid method, and we just apply it to minimize such a relaxation. So to get to some exponentially small volume, we need to run it for a linear number of steps. So after n not n steps, we will have something. We will have a region. Our remaining feasible region will be very small, 1 over n to n, basically. And so the key observation is that when you have a common set of size is small, you cannot have a non-degenerate set consisting purely consisting of integer vertices. So if that's the case, you can just recurse the same thing on the degenerate part of it. So this is the proof that I was mentioning about all the time. So when you have a set of size this small, you will consider all the lattice points in it or all the integer points in it. It has to be degenerate. It has to lie on a hyperplane. And the proof is very simple. Well, assume that's not the case if you have non-degeneracy. So if you have a simplex with vertices being all integral, well, you have the volume of this simplex is going to be at least 1 over n factorial, because you are just taking the determinant over an integer vertex. So it's going to be too big to contain in our target. So to summarize, once you do it for n iterations, you can identify all your remaining feasible solutions on a hyperplane. And that's because the minimizer has to be integral. It's a discrete problem after all.
So it's easy to find this hyperplane?
I'll get into that after. And once you get to a lower dimension, you can just apply the same trick. You have dimension n, so after doing it for n steps, you'll get to your minimizer. So the total number of iterations is just n squared log n. Each iteration costs you all the n time to compute this gradient. That's the only thing we did about submodular function. So overall, you can get a minimizer in qubit time. So it's not a difficult proof, but as you can see, just by using something very elementary about convex optimization, we can get this fantastic band for submodular minimization, which is n squared better than before.
I guess the natural question is what's the main difficulty why people haven't done it before? That sounds like something could have been done.
I think the main reason is
people
because
believe you can actually get fast thing as opposed to just.
Usually you can't get strongly polynomial.
I see. Okay. So people didn't really look in this weekly methodology much.
But even weekly polynomial, it seems like you get the best bounds.
Yeah, I would say that's because traditionally people in combinatorial optimization, they are not that familiar with convex optimization, so they missed this natural connection between the two.
But you also improve the cutting plane.
Yeah. Well, that's another story.
Yeah, that's a big story.
I see. So basically, before you would need to run ellipsoids, and you would have factor of n more.
No, so
Yeah.
there is Vidya in between. So,
Yeah.
so if you run Vidya, you get indeed this running time from the number of cores, but then the computational complexity is high.
Yeah.
They improved on Vidya for the computational.
So they get like some proxy for center of mass.
Yeah. You can
So to get this bound, you can just use a CG. But to get, so I didn't tell you how, yeah, it's actually something Sebastian asked before. This is an algorithm, but it only concerns about the oracle complexity. I didn't actually talk about the actual running time of the algorithm. Well, everything you can do in polynomial time, clearly, except this step. So how do you get the degeneracy? How do you get, can you get, such a degenerate hyperplane efficiently? I think the answer is no. So, if you want to implement it, you have to basically spend exponential time on this step.
Is that different from finding the approximate center of gravity, right? Yeah. Is it first, there's two steps. One, you need to find the approximate or
yeah,
you need to find the right.
You can approximate gravity, you can get that by as a consequence of, convex set sampling. So you can sample points in a convex set efficiently. So you can get an approximate CG, and that will still be good enough.
So what do you mean you need exponential time for that then?
So this is the Q result, the full result. We can get a fully polytime algorithm. So what I stated a few slides before, you can actually get an n4 time algorithm, but that you have to actually get into the structure of the submodular functions. So you actually have to do some, more classical combinatorial optimization stuff mixed with some convex optimization.
So what's the lower bound and the number of oracle calls?
I would say that's the biggest open question in the.
So what is it?
No one knows.
What's the best node, like n?
And just the trivial bound n. I think McCarthy in his MIT thesis proved a lower bound of 2n or something, so something slightly better than n. So in particular, we don't even know if we have lower bound of n or n. So it's the state of the art is pretty disappointing for this lower bound. It seems really hard to get something. I think it's n cubed. N cubed or n cubed, not n. Yeah.
Up to what?
I don't know, but here's the other thing. Let's say you're happy with just a certificate of optimality. So you give me a solution, how many oracle calls I need to find a certificate of optimality for such a solution. Even for that case, the best that we know costs n squared. So the smaller size certificate requires n squared oracle calls
That is true for
that we know about. Yeah, but
For example, can you get better upper bound for coverage functions? Oh no, coverage functions are trivial. Like you need some negative things. Okay, fair enough.
yeah, it depends
But
on
for special
how.
classes, for some interesting special classes, can you get something better?
For what? Upper bound. Min cut, for example.
Sure. Again, min cut is slightly.
Actually, one of the examples, one of the candidate lower bound example is the min cut, is the cut function, st min cut, st cut function. Yeah. Yeah. So. Yeah, I would say we don't really know anything yet, and I'll be very excited if there's any progress on the problem.
But this seems to be common, right? I mean, even for min cut problem, like finding and like checking their running times are still the same, right?
So why don't you finish up?
I think I'm pretty much done. Yeah. Yeah. So again, the main story I want to get across is just that you can get something better easily if you swap convex, if you swap linear with convex. So by going to the more powerful convex optimization paradigm, you can get something very easily. And there are other examples of this thing. So you can also do this for matrix intersection and submodular minimize and submodular flow. And recently, there's this work on K-server, which is kind of in the same spirit. So that's all I want to talk about today. Thanks. Yeah.
Okay. Just in the spirit of going from linear to more convex optimization, we have done this cutting plan with either ellipsoid or similar gravity, but just one cut. You add as a volume. I think there's a, in terms of optimization, non-smooth convex optimization, there's a cutting plan method. Basically, you not only just one cut, you keep all the cut. And then you build a polyhedral model of your thing, and then you minimize kind of within that a region bounded by all your previous cuts. I think this method may have a, I mean, in terms of course, you can imagine each step will cost way more. It's very few. But in terms of pure oracle complexity, I don't know if this will be actually improved on the.
So you have a better, you'll be the same up to asymptotics. Okay. So this ellipsoid method or this separation problem is really just about basically doing binary search in high dimension. So binary search, even in the, if your input is really bad, you have to take not n steps.
Okay. Asymptotic.
Yeah.
I'm just want, because I think one of the, in terms of lower bound, I think some of the cutting, weekly, some of the cutting plan methods actually achieve the lower bound for optimization.
Yeah, Intel, Aaron, and Santos have a paper on it.
Okay. Yeah. Good.
Yeah. So they studied the lower bound needed for journal cutting plane method, basically. Yeah.
So it seems like all the examples you presented, there is some sort of like common theme, right? I mean, the LPs sort of look like configuration LPs, and the dual was doing this separation oracle, and somehow you said that you can actually roll those things into convex program and solve it faster. So is this like a more general principle? Because I saw in this box that like Chandra had this paper where he also claimed something like that. You can solve convex, like if there was a configuration LP with exponentially many variables, then they can actually get sort of like almost linear time algorithms for this. Like he gave examples of ATSP and some.
Is it in? I think it's in Soda last year.
There is a follow-up paper. Okay, I don't know. Yeah,
okay.
One of these. Is that the thing? I mean, is that the reason why these things are?
So I think
or is there a connection between
the work of Chandra Chakuri and Ken Corbin, they used first order method. So it's not quite the same, but it's in the same spirit.
Okay. I actually think that there's like the common theme. Actually, even all the three problems for me look exactly is you have LP, but in lots of cases you can replace LP by instead of linear function, you replace it by a piecewise linear function, which is convex. Basically, lots of the constraint can be
that's basically
that way. That's exactly a piecewise linear function. But the good thing is that if you do that and you have no constraint or very simple constraint, then you can free to use this kind of.
Yeah, that's a good observation. That's actually, the common thing, to all the three examples.
Okay, then they're more interesting because in order to do that, in lots of examples, when you do this piecewise, it's always a max of something. So it's a structured piecewise linear function. Those structure are kind of ideal for nature of the smoothing, right? If you do some smoothing, I wonder if you could further get the acceleration, what's the first order method from smooth optimization.
So I think I tried to do it. I spent some time on it, but I think you can, I I believe you can do something cool for the econ problem I talk about. So instead of second order method, well, if you use first order method, can you get something?
Yeah, the basic example is if you use just non-smooth, you just apply a first order method, mirror distance or something, you got like 1 over epsilon squared convergence. Yeah. And if you have a smooth, purely smooth function, you'll get a 1 over square root of epsilon. But if you using smoothing over the non-smooth thing, you will get in the middle. You will get a 1 over epsilon. So it's just like there's a benefit. You can improve that.
So the difficulty or the challenge for the econ problem, you can get something easily just by using first order method. You can get something. It just follows from the guarantee. So the challenge is to get something meaningful economically. So to get like a bond.
If you use accelerator, I'm not like a lot of the step not have economic interpretation. It would be weird things like interpolation.
Yes, this one that he showed actually has this interpretation as Tatonement process. He's surprised.
For submodular minimization, I mean, I don't have a proof, of course, but I think it's impossible.
But you want log 1 over epsilon.
Let's say you want to solve approximate submodular minimization. Can you do 1 over epsilon? Like we have a paper where we can get 1 over epsilon square. I don't think can get 1 over epsilon, but I don't have a proof. That's just some gut feeling. Yeah. So for the second example, in the same paper we proved some basically some sort of acceleration type result. So for that case, you can get 1 over epsilon or even not 1 over epsilon. But as far as the setting goes, we also proved the bound we got, or the bound in Murray's lemma is actually tight. So we gave an example of that. So,
All right.
yeah, thanks for coming.